Okay, fine with me. So we start. So let me say a few words just before David starts. So we have the pleasure to receive David Hughes this evening. So he is a very active supporter of the festival since the first edition in 2001. I think he has attended all of them. That's probably some kind of record. Only a few of us did that. So as a bit of history, he received his PhD from University of Cambridge under the supervision of Nigel Weiss, if I'm correct, in 1984. Then he was postdoc in Boulder, in the Institute for Laboratory Astrophysics. And he was lecturer in University of Leeds, professor in Newcastle, and I think he's been professor in Leeds since 1995 now. He has been also visiting professors in Paris. This I didn't know, actually, in the Institut Henri Poincaré, as we say in French, and also at the Quant Institute in New York. So he has kind of a broad research scope of research interests, applied mathematics and numerical modeling of instabilities and turbulence, mainly, I would say, in the context of fluid dynamics and MHD, with applications to astrophysics and geophysical applications. Dynamo also, and you did a bit of fusion too, and I noticed you didn't put that on your website, David. So
well, it's in case someone asks me a question about, you know, the ion gyro radius or something.
Well, I'm sure you would answer.
I know it's not very big.
Anyway, so David is going to talk about magnetic layering, and the floor is given to you, David.
Okay, thank you, Xavier. Right, let's see. Can you see my screen? No, yes.
I think we can see it, but not full screen.
Yeah, let's try.
Yeah, we got it.
You go
Perfect.
Back to the beginning. Is that okay? You can see it? Okay, yes. Thank you, Xavier, for that nice introduction. Yes, I have indeed been to every festival. I have a campaign medal, along with a few others, but not many others. So this is what I'm going to talk about today. It's work that I've been doing with Nick for a very long time. Hate to think how long, but many years. But I don't think either of us has ever spoken about it at the festival, and it's been progressing all these years, and amazingly we have now submitted the paper a few weeks ago to AppJ. Okay, so I'm going to try and follow. I see on the website Guillaume was urging accessible and pedagogic presentation, so I'll do my best. That means some of this you will all know very well, but possibly not everyone. Okay, I'll get rid of this stupid bar off my screen. Right. So the main thing I'm going to be talking about is layering or staircase formation. And of course, many of you were at the KITP 3-month program recently. So we've had a lot of layering of late, just in case you weren't. So what is layering in general? So I mean the spontaneous formation of staircases or layered structures, which are regions of homogeneous turbulence, let's say, separated by sharp gradients. That's fairly vague definition. They might be gradients. Typically, they're gradients in lots of things all at the same time, like density or velocity, but they don't have to be. They're of interest. They're obviously of intrinsic interest because it's sort of order out of a turbulent, chaotic state, which of itself is always of interest. But primarily they're of interest, I suppose, because the transport through a layered state is very different to the transport through a non-layered state. And so if you want to parameterize transport, be it in a star or be it in a tokamak, then it's important to try and understand these states. And as we discussed at length in Santa Barbara, layering, you can get layering in a whole host of different physical systems. So here's one of them, possibly the most well-known, which is layering or staircase in potential vorticity, which in physical quantities really leads to banded zonal jets, like we have in this nice picture of Jupiter. Oh, now I'm stuck. What's happened? Whoops, sorry. Okay, it always does that. Here is a picture from EM et al., which is what's called the E cross B staircase, which comes in drift wave turbulence. And this is more complicated in a way. I mean, this has interactions not just between the staircase and between avalanching. And this is potentially very important in turbulent transport in tokamaks. I'm not going to be talking about E cross B or PV staircases. So what am I going to be talking about? I'm going to be talking about double diffusive convection and layering. So let me just set the stage for what I mean, what is meant by double diffusive convection. So double diffusive convection is motions in which the density depends on two components that diffuse at different rates. So the most well-studied is thermohaline convection. So thermohaline convection, the two competing gradients are temperature or heat and salt. So this is well studied in an oceanographic context. And the ratio, the diffusivity ratio is of salt to heat here is about 100th. So fairly small, but not outrageously small. And there is another parameter, which I didn't put here, which is the Prandtl number, which is the ratio of viscosity to thermal diffusion, which for water is about 7. Okay. In a different context, another well-studied double diffusive system is heat and some other, not salt, but some other gradient of composition. And in a stellar context, that is typically helium. And that is of importance in stellar interiors. For mixing in stellar interiors, there's been quite a lot of work on that problem. In that context, this ratio is smaller. The diffusion of heat to diffusion of helium to heat is smaller than this, and the Prandtl number typically is also very small. So it's a very different regime. It's also much harder to model numerically. So thermohaline convection is an unusual system in that you can almost model it exactly. Numerically, this is not an outrageously small number, and the Prandtl number is order 1. Modeling this properly with the true values is not, for the stellar case, is not feasible. Okay, so there's two sorts of motion that can go on. So if you consider the linear stability problem, then you can either have steady or oscillatory motions, and that splits the domain into two regimes, really. So you can have a stabilizing temperature gradient and a destabilizing salinity gradient. Okay, so if you think about that, if you have this situation and you move a little blob of fluid up, then because the thermal diffusion is so much faster than the salt diffusion, you erode the stabilizing gradient, but you maintain more or less the destabilizing gradient. And so the blob will come into more or less thermal equilibrium. It'll still be fresher than its surroundings, and it will carry on up. And so that's a direct or steady instability. If you consider the other, both gradients reverse, so you have a destabilizing temperature gradient and a stabilizing salinity gradient, then if you move a little blob of fluid upwards, then it will be it will lose its destabilizing component fairly quickly, whereas maintaining its stabilizing one, so it will sink. But of course, once it sinks back, well, it's been mixing with hotter fluid but saltier fluid, and so sorry, other way around, cooler fluid but fresher fluid. So when it comes back to where you kicked it off from, it may or may not be denser than its surroundings. If it is denser than its surroundings, then it will overshoot and you get growing oscillations. So this, whoops, sorry. This one is the steady motions is typically called the fingering or salt fingering regime because motions tend to be thin. The oscillatory regime in thermohaline convection, people call it the diffusive regime. In astrophysics, they call it semi-convection. They are essentially the same thing. So that's double diffusive convection. Double diffusive layering has been observed in the field, as it were, in oceans for a long time. Both in the salt fingering regime, which is when you get hot salty fluid on top, which is what you see, for example, in the Mediterranean, or the other way around, which is what you see in the Arctic regions. And layers have been observed, and they are long-lived and remarkably robust, actually. Kind of waves can pass through them and still live. What hasn't been observed until not long ago was layering in numerical simulations. Slightly surprising in a way, I suppose, because, as I said, it is possible to actually do the right parameter regime. But you do need a big box. So there's been a lot of work quite recently in the last 10 years or so, certainly by the group in Santa Cruz, looking at this. So, and you get layering in both regimes. Okay, so you can have an unstable temperature and a stable salinity, or the other way around. Both of them will lead to layering. So this is these are some pictures from paper by Stelmach et al. In the fingering regime. So this is as time advances. Okay, so it starts off with kind of fingering cells, if you like, and eventually these layers emerge. So what's being shown here is the temperature perturbation. Okay, and this is also from that group. This is layering in the diffusive regime, but with rather different. So this is more of an astrophysical motivation, where sigma, the Prandtl number, and tau, the diffusivity ratio, are small. Okay, obviously not as small as they would be astrophysically, but still fairly small numerically. Okay, and both of them lead to layers. So why is this? Well, okay. Oh, no, I'll come to why that is in a minute. So what's that got to do with magnetic fields? So as we'll see, as I'll try and explain, there's an instability mechanism called magnetic buoyancy, which you can also, under certain circumstances, consider as a double diffusive instability. So I'll explain why that is. Okay. So if these are important, if these magnetic buoyancy instabilities can lead to layering, then this has implications for transport modeling. Okay. And that's very important in stellar interiors. Yesterday, Pascal was telling us about mixing in stellar interiors, and she was talking about shear-induced mixing. So this is another thing to throw into the pot, really. This is magnetic buoyancy-induced mixing. I'll say later, there are an awful lot of mechanisms that are invoked for mixing. So this talk is not really clarifying. This is this is muddying the waters by adding yet more things to it, but something that we think is important to add to it. So the technique that we're going to use is to exploit an analogy between the equations describing magnetic buoyancy and those describing thermohaline convection. Okay, and I'll explain exactly what that analogy is. What I won't really do is to say why layering occurs in double diffusion, because nobody really knows, I think is a fair statement. And that I still think is true after many discussions in the KITP, interesting discussions, but I think it is still true to say that it's not really, there's certainly no consensus. I think people may have their view, but there is certainly no consensus view as to what explains double diffusive layering, and there is no consensus as to whether it has got anything at some broad level to do with, you know, the mechanisms that lead to PV staircases, or if it is a different beast altogether. So these are some of the mechanisms that have been put forward to explain double diffusive layering. So there's a nice review by Bill Merrifield, now probably getting on for 20 years ago, I think, and the book on double diffusion by Timur Radko also explains all of these things nicely. And these are possibilities. So first it was thought that it was sort of a mean field instability, almost what's called a collective instability of salt fingers. But we've seen that layering is not just in the fingering regime. It's conceivable that these are non-linear equilibria in a way that you can't get at through a linear instability branch. It might well be that in the oceans, intrusions driven by horizontal gradients are an important feature. They are clearly not the only thing, because in numerical simulations you don't have those. Okay, so that might be important, but you can get layering without that. Radko has put forward the idea of what he calls a gamma instability. Gamma here is just the gradient. Well, gamma is the flux ratio, the flux of temperature to the flux of salt. I'm not going to go through all of this. Essentially, it's a mean field instability. It's a horizontally, it considers horizontal averages, and it's an instability just dependent on Z, on height. I don't think it explains everything. It might well explain the change between a sort of homogeneous state on the way to layering, but it cannot explain everything to do with layering. Another take on it, which I think is, I don't know, promising, but I wouldn't really go more than that at the moment, is some sort of modification of the Phillips mechanism. So Phillips, back in '72, looked at the layering process in a stirred stratified fluid. And of course, it's all to do with the flux gradient relation, leading to a sort of negative diffusion. And there's a very nice model by Neil Barnforth, Stefan, who's here, and Bill Young, Stefan Royland Smith and Bill Young, which I think is sort of a K epsilon model. It's a two-component model. It's a two-component horizontally average model for the buoyancy and the energy, which shows, which has the Phillips mechanism in it, but much more as well, and shows how you can get layering. And it's an interesting question, which is still open, I think, as to whether a model of this sort can explain double diffusive layering, so a three-component model, if you like, but without forcing, but with the instability driven by the gradients. So Paparella and von Hardenberg they sort of looked at this, but really their model was essentially just the Barnforth et al. Model. So that's still an interesting open question as to exactly what is behind layering in this context. Okay. Better move on. I seem to be on slide 8. Right. So some equations to set the scene. So the equations, so what we're going to do, we're going to look at thermohaline convection and magnetic buoyancy and go from one to the other. So our basic system that we're going to work with is actually thermohaline convection, and we're going to map it onto magnetic buoyancy. The analogy holds in 2D, so I'm going to look at 2D motions, okay? So these are very simple equations. So these are the 2D equations of thermohaline convection. So since they're 2D, you can use a stream function where there's one component of vorticity, which is minus del squared of psi. Oh, yes. So there's a notational issue because I know plasma physicists don't use psi for the stream function, but fluid dynamicists do. So psi here is the stream function. There's three equations: vorticity equation, temperature equation, and salt equation. So this this big bracket here is just d omega by dt plus u dot grad omega, written as a stream function. There's two components to the buoyancy term, right? Or the curl of the buoyancy term. There's a temperature gradient and a horizontal temperature gradient, horizontal salt gradient. The viscosity term, and this parameter is 1 over the Prandtl number. Okay, so that's like the canonical vorticity equation for double diffusive convection. The temperature equation, advection of the temperature. These are perturbations. This T is a perturbation temperature. So this is big d by dt of T. This is u dot grad T bar, and this is kappa del squared T, and all the things have been scaled out. And this is d by dt of S is u dot grad S bar plus, well, kappa S del squared S, which scaled becomes a tau. Okay, so these are nicely symmetric. There is a diffusion of T only in the T equation. There is diffusion of S only in the S equation. There is both T and S in the vorticity equation. There are 4 parameters: Rayleigh number, salt Rayleigh number, Prandtl number, and diffusivity ratio, which we've already mentioned. So Rayleigh number is some measure of thermal driving. Positive Rayleigh number, thermally unstable. Salt Rayleigh number is some measure of solutal driving. Positive RS is solutally stabilizing, okay, in this convention that I got it here. These are just coefficients we needn't bother with too much. Okay. Whoops. So this is just what I said earlier, really. This is the stability boundary. I kind of said this. So there's 2 quadrants of note. There's the salt finger quadrant, which is Ra negative, Rs negative, where you can have salt fingers. There's the diffusive regime, where both Ra and Rs are positive. You can have oscillatory instabilities. There is a quadrant here where everything is unstable, except for some tiny little bit down here. And there's a 4th quadrant, which is absolutely stable, okay, because both gradients are stable. Okay, so I should have said, but forgot. In those simulations that I showed earlier of layering in thermohaline convection, they have, and indeed just about all, possibly all, I'm not sure about that, but certainly most simulations that have exhibited layering, numerical simulations, have considered an unbounded domain. And that's probably why they were not seen earlier, because the boundaries were important. So what does that mean? It means that you have perturbations are periodic, not just in the horizontal, but also in the vertical directions. Okay, so there are boundary conditions, but they're just periodicity in the vertical. That minimizes the effect of the horizontal boundaries and seems to be very important in getting these layered solutions. One imagines that if one took a big enough domain, then one would get layering regardless of the boundary conditions. But we also are going to adopt these boundary conditions. So if you adopt these boundary conditions, then there is no length scale. You know, the standard length scale when you do this is D, the length, the depth of the layer. If there is no layer depth, then you have no D. So you have to adopt an intrinsic length scale, which this is the intrinsic length scale. Okay. And well, you can just go through it. They look slightly different, the equations, because there is no RA and RS. There is just a ratio of RA and RS, which we define in this way with mod signs, and we put the signs in here. Because you can see if you didn't have the mod signs, then this R0 is the same in the first and the third quadrant, because you flip both signs, then you end up confusing the issue. So this is how they are done. It looks as if you've lost a parameter, interestingly, because only the ratio matters. Of course, that's not quite true, but that's how it looks. Okay, so this really is what we're going to solve. Okay, so the density ratio occurs here. Okay, right. So what is magnetic buoyancy instability? Why might it be considered double diffusive? So magnetic buoyancy instability has been studied for many years. I think the first study of it is by Newcomb in '61. Who, in a very nice paper, who looked at it from an energy principle. In astrophysics, it's often called the Parker instability. Parker looked at it in '66 in terms of the instability of the interstellar medium. Okay, how does it work? So it's slightly more interesting than the, okay, if you don't have, it's interesting even without diffusion, magnetic buoyancy. So unlike thermohaline convection is not interesting without diffusion, because it just says that if it's top heavy, you'll get instability. And if it's not top heavy, then you won't get instability, but that's a sort of statement of the obvious. Whereas magnetic buoyancy is interesting without diffusion for the following reason. If you take a flux tube or a parcel, fluid parcel, and you do the kind of normal Schwarzschild arguments, you lift it up and the pressure equilibrates, etc., then you get this condition for instability. Okay. Okay, this is an important condition here, that I'm only considering 2D modes. Okay, magnetic buoyancy gets super sneaky once we become 3D. So here we're just being 2D, no bending of the field lines. Okay, and so the criterion is just this. You need a group. So why it's interesting is because you could have n squared. N is the buoyancy frequency. So you could have n squared positive, which means it's essentially sub-adiabatic. But you can still have instability if B over rho falls off sufficiently rapidly with height. Okay, so this is first in Newcomb's 1961 paper. So the two competing gradients are B over rho and the entropy gradient, if you like, P rho to the minus gamma. As I said, this Parker put it forward to do with the interstellar medium. Now it's often also invoked as the means by which, for example, the solar magnetic field gets broken up in the tachycline to give rise to the flux tubes that we see at the surface. Okay. But at the moment, I haven't mentioned diffusion, but it's an instability of some interest even without diffusion. Okay, but what is important to, in terms of this analogy, you might say, how are you going to get an analogy? Because magnetic buoyancy is inherently compressible phenomenon, right? So you need the full works really to explain it. Whereas double diffusive convection, as we described it, is just well, you can describe it within the Boussinesq approximation. So it seems a much simpler system. So in order to, can we explain magnetic buoyancy in terms of a reduced set of equations? So this is, well, I think this is quite interesting. It's a little bit of a tangent to what I've been saying, except that it will help explain where the system of equations come from that we're actually going to study. But I'm not going to go through all the details. It depends whether you like epsilons as to whether you like this sort of thing. I quite like epsilons myself. So magnetic buoyancy is important if magnetic pressure fluctuations normalized are comparable to density variations. Okay, if magnetic pressure matters, that's when magnetic buoyancy matters. And it turns out, if you go through all the equations, and there's a heck of a lot of algebra to lead to this, if you consider the perturbations with a length scale along the field, I know I was saying we'll consider 2D, let's just relax that for the minute. If you consider motion along the scale of LB, then this is the crucial relationship that you need for magnetic buoyancy to be important. That LB squared, the perturbation along the field, must be of the order or greater than HP. HB is the magnetic field scale height. HP is the get it right, pressure scale height. Okay, and that's very important. So there's two parameters one normally thinks of. There's D over H, and there's delta rho over rho. So the D over H is layer depth over pressure scale height. Delta over rho is density variations over some representative density. Okay. Now it turns out you can get various approximations that depend on these parameters. Okay. Now why, and we've been looking at this recently. By we, I mean Frederick Belczynski and Evi Casale and I. And what prompted our interest was, as we'll see, if you want to put magnetic buoyancy into the Boussinesq equations, you have to jump through a lot of hoops. It looks as if you don't have to jump through any hoops to put magnetic buoyancy into the anelastic approximation. But is that true? Is it by not jumping through the hoops, something has been missed? Okay, so that's what we were looking at. So magnetic buoyancy in the anelastic approximation, for completeness, the anelastic ordering, D and all the H's are the same. Okay, so the layer depth, all the scale heights are the same. Epsilon 1 is order 1. Epsilon 2 is small, and it's valid for atmospheres close to adiabatic. Now, the total pressure variation, the magnetic pressure variations of the same size, and you might think, okay, but there must be some consistency condition. And the consistency condition for the adiabatic, for the anelastic approximation, sorry, is that the plasma beta has to be of this size. So the plasma beta is large, so the field is weak, and it has to be weak of just the right amount of weakness. Okay, so if you decided to study a case where epsilon 1 was order 1, but you said, oh, I'm going to crank up my field strength, then you would not be allowed to describe that within the anelastic approximation. Okay, so all these things hang together in a very delicate manner. So this is, you think, okay, what about Boussinesq approximation? This is the Boussinesq magnetoconvection. This is much studied, probably going all the way back to Chandra. The total pressure perturbations and the magnetic pressure perturbations are tiny, epsilon 1, epsilon 2. And in this approximation, the plasma beta is huge. 1 over the plasma beta is epsilon 1, epsilon 2. So this is what you get if you just come along with from the Boussinesq equations of convection and you plonk in the magnetic tension and the induction equation. This is what you get. And they're only valid, but you never actually think, well, you may or may not think, but it's never often stated when they're really valid. They are valid when the plasma beta is this, 1 over the plasma beta is this tiny number, okay? Magnetic buoyancy doesn't come into them because the all the pressure variations, the total pressure, but also the gas and magnetic pressure variations individually are tiny. Okay, so there is no, if you take the equations that Chandra has in his book, they do not include magnetic buoyancy. Okay. So you might think, wow, they're in the anelastic approximation. How do I go from anelastic to, can I go from anelastic to Boussinesq and keep them in? So yes, you can, So Spiegel and Weiss looked at this, and Caulfield looked at this. So there's a weak field gradient, magnetic buoyancy, magnetobucinesque approximation. And as I say, you have to jump through hoops. And if you really want to do it asymptotically correctly, you have to scale, you have to have different scalings of your length, parallel and perpendicular to the field. Total pressure variation is tiny, but individual pressure variations are not as tiny. So the gas and the magnetic pressure variations are order epsilon 2, but added together, they are smaller. Plasma beta is large, but not nearly as large as it used to be. Okay, it has to be this ratio. So to get magnetic buoyancy into the Bucinesque approximation, you need this plasma beta and you need this scaling of lengths, okay? Or alternatively, which is not in Spiegel and Weiss, actually, you can go for a stronger field gradient, but a weaker magnetic field, okay? And this is how they come into the magnetobucinesque, this is how to get magnetic buoyancy into the Bucinesque approximation. So it is not straightforward. Okay, right. So what are the equations of magnetic buoyancy in 2D? So some of these subtle scales and issues that I've just been talking about, they don't actually arise. We're going to do 2D. So we have a vorticity equation where now we have temperature and magnetic pressure variations contributing to density. We dot the induction equation with B, and we have a magnetic pressure equation, which looks pretty good. It looks like a salt equation. The key gradient, as we might expect from what we were saying earlier, is B over rho. And we have an energy equation, which does not look like the temperature equation because it has magnetic pressure advection on the left. Okay, the key gradient is the entropy gradient, subadiabatic temperature gradient. Okay. And it has diffusion of temperature. So they're not quite in the canonical double diffusive form in that case. So we make them by adding a combination of the delta PM to the delta T equations. So this is now the relevant equation. So the price you pay for having a nice equation is that you have weird variables. Okay, so in some sense, these are what Nick likes to call the natural variables for this problem. I'm not sure they're quite so natural. And they're natural once you've got the equations, that is true. And so these variables are a combination of the temperature perturbation and the magnetic pressure perturbation and the diffusion tau, the diffusivity ratio tau. And the key gradient is a mixture of the subadiabatic temperature gradient and the B over rho gradient, and also with tau. Okay. So if you write, so the mapping is essentially the magnetic pressure variation becomes minus salt. And this funny combination, this hybrid quantity delta T star, becomes temperature, normalized by the funny gradient. Okay, so if you have a Rayleigh number, so this is okay. This is a B over rho Rayleigh number that you might expect, but this is an unusual Rayleigh number because it's a combination of gradients. Then you get back to the thermohaline convection. So that is the mapping between them. But you might say, this is what I would call natural Rayleigh numbers, okay? Then if you, as we've seen, in the absence of diffusion, the key gradients are B over rho and P rho to the minus gamma. So you might have said, no, surely then you could obviously define Rayleigh numbers in this sense. So this is essentially just as like on the previous page, this is a B over rho gradient, and this is a subadiabatic temperature gradient Rayleigh number. So these RT and RB are linked to the salt Rayleigh numbers, RA and RS, through this linear relation. But this is interesting because this changes the stability diagram to this. So this is not new, this is quite old. but it's important for what I'm going to say. And you can see why is it interesting? Well, obviously it's interesting because this line, this instability line, has a negative slope and comes down into the fourth quadrant. And the fourth quadrant is stable, stable, right? Both gradients are stable, if you like. And so that is unusual. And it's readily satisfied. The condition for this line to have a negative slope is that the sum of the tau, the ratio, which is now eta over kappa for the magnetic problem. Sorry, I should have said that. So tau is meaning two things in this talk. If I'm talking about thermohaline convection, tau is kappa S over kappa, and the salt over heat diffusion. If I'm talking about magnetic buoyancy, then tau is eta, the magnetic diffusion, over kappa. So astrophysically, tau is minuscule, the Prandtl number typically also, and so this is a very small number. Gamma now is the standard gamma, the ratio of specific heat. So this number on the right is about 2/3. So this is readily satisfied astrophysically. So you do expect instability in this, quote, stable, stable quadrant. You might think, how come? So what happens and why it's different to the squished by the stronger field, because the field is increasing, well, technically b over rho, but let's think that the field is increasing with height. And so it squeezes the blob, and so it gets heated up. It's still denser. Of course, it's denser because we've proved that there's no instability in that quadrant in the absence of diffusion. So it falls, but it sheds heat because of diffusion. And, you know, if the phases are right, it can be denser than originally and will overshoot. Now, it is possible to obtain steady nonlinear solutions in this quadrant. Nigel Weiss and I looked at this many years ago, which of itself is quite surprising, right? Because the instability is an oscillatory instability. Okay. So we're asking yet another question here, which is, can we obtain layered solutions in this stable, stable region? Okay. Just a slight diversion. We could recombine the equations in a slightly different way, like this. I write them like this just because those of you that went to Edgar's talk a few weeks ago on binary convection, he had equations which were these equations. He did actually have these two to be the same. Kappa and kappa tilde were the same in his talk. So this now looks very much like binary convection. So all those nice things that Edgar talked about, isolated solutions and things, presumably are hidden somewhere in this, not even hidden, but they are there in this magnetic buoyancy system. Have to be a little bit careful, of course, because we're combining the important thing in Edgar's talk is that his two quantities, what I called delta sigma and delta lambda, had different boundary conditions. And you can see that that would be slightly unusual here in that, you know, because delta sigma involves delta PM, and if I were to want delta lambda to have a different boundary condition, it involves delta PM. So, well, you could have you could have a funny boundary condition on delta lambda. So it's plausible that some of those nice things that Edgar talked about are also applicable to this system, but we haven't explored that. Okay, so these are the equations the magnetic buoyancy also has equations, of course, in an unbounded domain, and you can go from one to the other, but I don't think we need to go through all the gory details, really. No. Right, onwards. So what we're going to look at is some numerical simulations of the nonlinear evolution. Okay, so what we really do is solve the equations of 2D thermohaline convection. In the diffusive regime, everything I'm going to be talking about is in the diffusive regime. The analogy, of course, holds in the fingering regime, but these two runs I'm going to talk about are in the diffusive regime. We're going to have small sigma and small tau. Sigma is the Prandtl number, tau is the diffusivity ratio. These are not astrophysically small, but they are small because one is there's a balance, of course. One wants huge domains, small diffusivities, and finite time of computational runs. So there is a balance to be had. The domain size, in terms of that wacky unit that we use to scale the length, remember, is 100 pi times 200 pi. That doesn't mean all that much. A better way of thinking about it is how many of the most unstable fingers do you get across the domain, and it's of the order of 20. Okay, that's the resolution. We solve the thermohaline problem and we map back to the magnetic buoyancy problem after the fact. Okay, a key quantity is where is this fourth quadrant boundary? Okay, the fourth quadrant is the stable quadrant. So, oh, no, I don't want to flip back through all of those. So this inequality is between the RT equals naught axis and the stability boundary. Okay, so this is all the points in, if R naught, yeah, you might be thinking, why are you using R naught inverse all the time? Sorry, that's just because what people do. So R naught inverse occurs, well, this is the magnetic buoyancy. It always occurs here. And you might think, well, that's silly. Why don't you call it something else because of the inverse? But people don't. So we're just sticking with convention. So this is the RT equals naught line, and this is the stability boundary. So astrophysically, you think, okay, tau is tiny. So the left-hand side is gamma over gamma minus 1, which is essentially 2.5. And the right-hand side is some immense number because sigma is tiny on the top and sigma plus tau is tiny on the bottom. Okay, so there's a vast regime of R naught inverse that lie in the unstable regime in the fourth quadrant. So we're going to look at two cases. One is 1.5. So that is in the first quadrant. And the other is 4, which is in the, that's wrong, isn't it? This should have been, sorry, that's fourth. I can't count. That's the fourth quadrant. So in terms of the thermohaline problem, you think, well, okay, you've changed a parameter, so what? I mean, do we expect anything massively different in the thermohaline problem between R naught inverse 1.5 and R naught inverse 4? Well, probably not in some sense. However, in terms of the magnetic buoyancy problem, you've changed everything completely because you've gone from a case where your two gradients, one of them is destabilizing and one of them is stabilizing, to a case where, at least stabilizing in quotes, if you like, to a case where both of them are stabilizing. Okay, so mapping back to the magnetic buoyancy variables, you do expect to see something different in these two cases.
Can I ask a question, David? Is it okay?
Yes. Yes.
Or do we ask at the end, or can I ask now?
You can ask now, Christoph.
Okay, thank you. So what about the first case when you have R0 to -1 equal 1.5? From the inequality above, this is stable, isn't it?
No. It's just not in the fourth quadrant. So this line, no. So that inequality that I just showed is this. If you can see my cursor.
All right, I see. Okay.
This region.
Okay. Yeah.
So one of the simulations. So the R naught inverse 1.5 will live up here.
Right.
And the R naught inverse 4 will live down here.
Okay, it's just not this quadrant. Thank you. Yeah.
So this is, sorry, I know we've seen those before, but this is, I've taken the signs out now because we're really in one. In terms of the thermohaline problem, we are in the first quadrant. Okay, so where before I had signs of dt by dz and ds by dz, now these are definite, these have definite numbers. If you remember, there's a minus tz bar in here and a minus sz bar in here. So they both became plus ones. Okay, so these are the set of equations we solve. Okay, and then we map to the thermohaline problem through this transformation. I know I've been through this just to remind you. So essentially salt and magnetic pressure variation is more or less minus salt. And temperature, though, is this funny delta T star combination. The variables you might want to plot are delta PM, that's okay, that's just scaled salt. Delta S, which is essentially the variation in P rho to the minus gamma. Now that is a funny combination because it's very hard to, well, it's got various things in it. It's got delta T star in it, but it's also got delta PM in it. And the gradients that you're interested in are the B over rho gradient. Well, the B over rho gradient is fine. It's got B over rho of the basic state. That's what this alpha is. Don't worry about that. And it's got, once it's all scaled, delta PM just comes in here. So this is just like salt. This would be like the salt is the salt background salt gradient plus the salt perturbation. So that one, field and salt, give or take a sign, are the same thing. But the thermodynamic one, if you like, is all over the place in that the entropy gradient has a background gradient which depends on beta star. Beta star depends on beta, the subadiabatic gradient, and alpha, the B over rho gradient, and this bit of alpha. And then the perturbation to that also has delta T star, which has delta T and delta PM in it, and delta PM. Okay. So we go from this nice set of equations, beautifully clean set of equations, and then we move to this slightly more complicated system. Okay. Some of the results I'm going to show, I hope it won't be confusing. I hope it's clear what I've done. Some of them I'm going to show for the thermohaline problem. Some I'm going to show for the magnetic buoyancy problem. Some I'm going to show for both. This is what it looks like at the beginning. This is not relevant for layering, but it's kind of pretty picture. So this is, as I said, there was of the order of 20. So the most unstable mode is an elevator. It has no variation in Z. It's an exact solution of the nonlinear system, of course, because there is no advection. J of psi del squared psi vanishes for an elevator mode, and so there is a perfectly good nonlinear solution which grows forever. Thankfully, it's unstable, and this is its instability. So this was looked at a long time ago for salt fingers by Melvin Stern and Judith Hollier. For the oscillatory case, it's a more complicated problem, of course, because it's a Floquet problem in both time and space. And my student Thomas Goodfellow looked at that. The upshot of all of that instability is that you get a fairly well mixed state. Now, this is the same state. The top three panels are for the thermohaline problem, and the bottom three panels are for the magnetic buoyancy problem. So the vorticity is the same. The salt is more or less minus the magnetic pressure. So blue goes to red and red goes to blue. But this one is more interesting because this, remember, the entropy perturbation is a combination of these two. Now, what you can see and what you expect in the thermohaline problem is that gradients in salt are sharper than gradients in temperature. Okay. Now, it's not quite clear a priori what the gradients in delta S should be, but they are obviously much sharper than gradients in temperature because they come from a combination of these two. But the mean profiles at this stage have not really changed. The mean profile is, the basic state profile is just linear, and it's more or less linear. That's just a snapshot, but it's certainly not showing any staircase tendencies at this stage. Okay. Now, as time goes on, the kinetic energy just increases and increases as the system evolves. And these three red lines correspond to where I'm going to show pictures. So this is about the first time that you would say staircases were emerging. And this is an incredibly turbulent system. Okay, this is a very turbulent staircase system. And again, in the thermohaline problem, it's in a way, as you'd expect, the gradients in the salt are sharper. In the magnetic buoyancy problem, that's not true because they're a combination of these two. But these layers are not super robust. I mean, it is such a turbulent system that these are destroyed by energetic motions of the convection, really. I mean, there are models of layer merging, but this is, I think this is like turbulent destruction of the layers. And you lose the layers one by one. So here you might say you've got 4 layers, 4 staircases. And here you've definitely got 3. So this is just at a later time. Oh, sorry. These are both the magnetic buoyancy problem. This is at a later time, and this is at an even later time. And if one were to keep going, and this is very common in these systems, you end up with 1 step. So that's an interesting problem. Even in the non-turbulent thermohaline, well, much less turbulent thermohaline runs at less extreme parameters, the final state typically is 1 step. And so there is clearly important physics missing in the numerical simulations. In terms of the observations in the oceans, there is a well-defined step size and it is robust. Okay, and that is not, I mean, there's lots of things it could be, of course. It could be, Businesky is not right. There is an external, there is another scale in the basic state. So, but all of these run down essentially to 1 step. And these are the mean profiles for this run. So this is the first quadrant run, okay. And you can see their staircases. They're quite well defined in density. They're reasonably well defined in salt or B over rho. And they are not quite so well defined in P rho to the minus gamma or in entropy, okay. What about fluxes? Because fluxes are very important, turbulent fluxes. So the top 2 are the turbulent fluxes, the vertical flux of temperature and salt. Okay, so this is for the thermohaline problem, and there is an upward flux. So this is a volume average. There's upward flux of heat and salt. You would expect, therefore, a downward flux of delta PM, magnetic pressure, which is what you get because magnetic pressure is essentially negative salt. And the other one, like a priori, it's not quite clear what you would get, in my view, because the upward flux of entropy, if you like, entropy perturbations, comes from the combination of the heat and salt fluxes. It turns out that the turbulent heat and salt fluxes are roughly comparable, and we've also got tau very small. So if you work it out, this thing here is gamma times WT minus gamma minus 1 times WT, if WS and WT are the same. And so they all turn out to be of the same sign. Okay. That, at least to me, was not obvious in advance how it would come out. So this is a nicer, right, sorry, can I just have 5 more minutes? Sorry. This is the other case. This is the 4th quadrant. So this is this is a nicer staircase. So we're nearer the stability boundary. We're further away from the top heavy boundary, and we're nearer the stability boundary. Okay, and the layering, you can see how the layering forms here by eating in or eroding the homogeneous region. So this is going down is increasing time. This is all for the magnetic problem until the first fully layered state is here with, I don't know, 6 or 7 layers. Okay, and these are much nicer layers than for the less turbulent layers. Okay. So now comes the bit where you think what's going to happen, because this is the thermohaline staircase for that problem. So we're in the first quadrant, so the temperature decreases with height, right? It's thermally destabilizing. We're solutally stabilizing, so the salt falls off with height. You get a sharp salt staircase and a slightly less sharp thermal staircase, because kappa S is much less than kappa, and you get quite a nice density staircase. Okay. Now you say, well, what's going to happen? So if we look at P rho to the minus gamma, B over rho and rho. So B over rho is just minus salt. So that's okay. We get a quite sharp, so B over rho, remember, is decreasing with height. Okay. But this one is also stable. So then the original gradient, of course, is stable. So the only way that it can get itself to convect, if you like, is to be so stable within the interfaces that it allows a slightly weaker backward-facing unstable bit in between. So you get a very sharp backward-facing entropy staircase. Okay, and that tallies a little with what Nigel and I found in terms of steady convection in a system with rigid lids in this same regime. Okay, so that's how it does it. Again, you get a positive entropy transport and a negative delta PM transport. Okay, so what does it all mean? So interestingly, you can get layering in the stable regime. So this is of potential importance in mixing in radiative zones, stellar radiative zones. Normally, there are lots of literature on mixing in stellar radiative zones. Normally, mixing processes that are put forward, for example, like Pascal was talking about yesterday, shear and things, then normally inhibited by field. So here the field is driving. Okay, what we don't know is, how does it all hang together for truly astrophysical values of sigma and tau? This is a picture from one of Jean Bauzan's paper, just to show how messy the problem is, really. So this is, I'm not sure quite what all the arrows mean. So these are just the various means by which one might get mixing, meridian circulations, gravity waves, convection, well, even if you don't have convection, there is still an awful lot of stuff going on. So as I said at the beginning, we have not really clarified. We have just added another box to this mess, but probably an important box. And also it's reading the literature on red giant branch stars, it seems that none of these mechanisms are enough to explain the mixing needed to explain the observations. And so there's a paper by Bousseau et al. And they put forward mixing by flux tube mixing. They say, you've got a buoyant flux tube and it will rise and bring stuff up with it. We're putting forward a different, which is also magnetic buoyancy in a way, but we would say that our mechanism here might also be important in that case. okay, everything here is based on an analogy, and the analogy is a very restrictive one. It's 2D motions in the magneto-Boussinesq approximation. So what if you relaxed either of those? My feeling is that if you relax the 2D in the 3D, it would still hold, because 2D, even though 2D and 3D thermohaline convection can be very different, 2D and 3D magnetic buoyancy is not so different, because of course the field provides anisotropy. Okay, so even 3D magnetic buoyancy instabilities have a strong 2D component, if you like, long wavelength along the field. Going beyond the Boussinesq approximation, that is clearly also important, and it's important because it starts introducing other scales into the problem from the off. Frederick Wilczynski has started looking at that. That's a very interesting problem. And as I said, there might be implications for layering in binary fluids, because it looks like a very similar system. Okay, I apologize for rambling too long. I'll stop there. Thank you.
Well, thank you very much, David. Well done. So we have time, plenty of time for questions. I don't see any question raised so far. Here I see Guillaume, so please, Guillaume.
Okay, well, I have several, but maybe one first. How much do you think this is all robust to shear, noise, or whatever? You know, if you wiggle the thing a little bit, how much does it resist?
Yeah, well, of course, I don't know. I mean, that's interesting, because Pascal yesterday gave a talk on shear, in which the question is this robust to magnetic fields? So now when you give a magnetic field talk, the obvious question is, hey, is this robust to shear? That's, I mean, the honest answer is, I don't know. And it's going to, well, I suppose it depends. Of course, it depends on the geometry of the shear relative to the geometry of the field, doesn't it? So if the, you know, if the shear is, yeah, and then it's going to depend. So suppose you had shear along the field direction, that's going to lead to instability. Then it's, you know, it's going to depend on things like the magnetic energy and the magnetic Reynolds number, right? So I would say that weak fields can certainly change things weak fields can change hydrodynamically, can change things hydrodynamically quite readily in a very highly electrically conducting case. So in a way, this might be a little more robust, but yeah, you'd have to do the analysis to see how it would work. I mean,
but I'm asking because maybe I had the wrong impression, but I had the impression that, for instance, the fingering regime versus the diffusive regime, well, the fingering one was much more susceptible to be destroyed by any type of noise or shear or whatever, and the diffusive one more robust. And since you're based on that analogy, would you have something like that also? And
okay, I mean, what is clear, although this is a kind of roundabout defense, what is clear is that these things they measure in the Arctic, which is in the diffusive regime, the staircases they measure there, are incredibly robust to stuff, you know, to waves passing through them and things like that. So in nature, there is a certain robustness in that regime. That is true. That's not a very strong defense. I mean, there might be, I think Pascal probably has done stuff on shear, and well, again, it's not really, even if there is work on shear, you have to be careful, of course, because once you go beyond the out and out analogy, then you can't really apply it.
Mhm.
So it's not clear. That's an interesting point as to whether there is an analogy between shear thermohaline convection and sheared magnetic buoyancy, for example. There may be.
Okay. May I have a second one or later?
It's fine by me.
Okay.
Well, please go ahead, Ian.
Okay, so the magnetic buoyancy is probably a mechanism that is probably going to be destroyed if you have vigorous convection. So it's probably going to apply more to the radiative interiors, right? If I got that correctly.
Yeah, that's right.
So probably applying it to the solar tachocline. Is there, I have, I guess, a twofold question. Is there a possibility that you may get a layering all the way to the core due to those instabilities? Is that ruled out by helioseismology? And second question is, would this layering in the radiative zone help you to confine the tachocline?
So in theory, yes, you could get layering throughout the radiative zone through this mechanism. It's not ruled out by helioseismology because you'd have to work out, you'd have to work out whether there was a consistent layered state that was in a more or less uniform state of rotation that, that was still consistent with helioseismology. So I think to confine, I would have thought it would be good at confining. How people talk about confining the tachocline underneath at the moment is just by some sort of magnetic field. So it seems to me a layered state would do a better job of confining the tachocline than a non-layered state. Yes. But I wouldn't really like to go beyond that. In terms of your first point, yeah, in the convection zone, it's, the convection will dominate, and that's that. Yeah.
Okay. I think, is that okay with you, Guillaume?
Oh, I'm sorry, I said thanks. Yeah.
Yeah, okay. Pat, I think you're next in line.
Yeah, I think I'm next, yes. So a number of questions. Why doesn't Bly work? What is what's the issue there? One would think to me, Bly is as good as the mixing length, right? And is the issue the absence or the irrelevance of a gradient dependent emergent scale, or is there another reason?
Well, okay. So I don't know that Bly doesn't work.
But you certainly don't paint a very rosy picture of it. And then I think that Paparella and von Hardenberg take some liberties, shall we say. So
yeah, Paparella and von Hardenberg, essentially, they are just Bly.
Yeah, exactly.
But they might, okay, the Paparella and von Hardenberg argue that there is a large, so how they argue it is that, at least in the salt fingering regime, once their salt fingers have done, they've done the initial instability, they then say, based on their numerical simulations, and this I think has some truth to it, is that there is a sort of clumping.
Right.
And the clumping then sets an external scale. So that scale then becomes what in Bly is D, the scale of the stirrer.
Mm-hmm.
Okay. And then so they say, oh, there is a scale which is different to an emergent scale. But then they just lift Bly. Okay. So what, right. So why is Bly tricky, I would say?
Right.
Is a few things. So if you look at the Bly paper, then the nature of the force, I don't know if Stefan's still with us, the nature of the forcing is very crucial.
Of course.
Right. In that they have, that they look at three cases, for example. One is constant power, constant force. Neither of those really give you the right flux gradient relation. And something like equipartition, I can't remember quite what they call it, the one which gives you the nice S-shaped curve. Okay. So in the Bly problem, you're trying, without, if you really wanted to try and do it without too much fudging, then you might think you'll start with just gradients, right? You won't have an external force.
Mm-hmm.
You just have gradients. You have gradients of heat and gradients of salt. And then you've got to think also very carefully about the emergent length scale, because in Bly it's fine because everything is stably stratified. And so the Osmodov scale is fine. You can just define it in terms of the buoyancy gradient and everything's hunky-dory. Whereas in convection, then that also becomes problematic because there are going to be places where you're thermally unstable, in which case you've got to come up with some other length, some mixing length, let's say, and cases where you're thermally stable, or BZ is positive, where you're going to have a different scaling. So you've got to transition between those two. So that is also sneaky.
The party pooper.
Yeah, and so I'm not saying it won't work, but I'm saying it's not straightforward to move from one to the other. And so my student Paul he's looking at this, and so there are ways of going between what you might call pure Bly to pure DDC Bly in steps, which is sort of the better way of looking at it, I think. So it might work, but even within Bly, it's kind of interesting that you need a very specific forcing mechanism. Whereas you might think, well, I don't know, if you do an experiment, if you have a stably stratified fluid and you stir it, is it really that dependent? Is layering really that dependent on the stirring? Or is that a kind of, a feature of the model, which is actually in reality, it's more robust than the model? I don't know.
One could imagine, though, the energy liberated from the instability of the elevators as the de facto stirring, right? I mean,
Yeah. But then that's right. But then it's a question of how you parameterize it.
Right. No, of course.
And so I'm sure one could write down a 3-component Bly model with some forcing that will give you layers. Now, but whether you've taken too many liberties, then I don't know.
I understand. So I had another question. Speaking of models, I mean, I'm puzzled by the impasse in models in this problem, as opposed to not just to Bly, but also to that genre of ideas seems to have been very successful, right, in games with drift waves and so forth, as we did with a Shurvan and all some time ago, and so I'm puzzled by why not here. And it raises the other question of Edgar demonstrated, I think, or argued the utility of the Swift-Hohenberg model as a nice structural nice structure for understanding what's going on in the binary convection. And given that the system is so close to the binary convection, I mean, what's your outlook on games with Swift-Hohenberg? I mean, I think one of the interesting points of Edgar, which is no surprise to those of us in fusion, was he made a distinction between negative diffusion and sort of off diagonal things, which we would call a pinch, I mean, in our language, which can clearly be going on here too. I mean, one gradient doing basically driving an up gradient flow in the other channel. So the whole Swift-Hohenberg thing strikes between Swift-Hohenberg and Bly, one should be able to come to grips with this problem. Sorry to run on, but.
Yeah, maybe. Yeah, it depends. Okay, I mean, Swift-Hohenberg, of course, Swift-Hohenberg is just a model. It's not derivable from the equations, right? And so, well, I think Edgar did do, except maybe I think there was one case. Okay, but in general, it's just put forward as a model. So in that sense, it's as good a model for this. And so in terms of the things that you're going to get out of Swift-Hohenberg, like pattern formation and things, they are there. They are there in this system. Because it's the same system, right? So at that level of model, if you're interested in pattern formation in magnetic buoyancy, then you could probably say something by a Swift-Hohenberg. Okay. In terms of binary fluids, as I said, you have to be in what we've done, we have got rid of all the difficult problems because we're not diagonal, but we can be diagonal. Just as Edgar could have been diagonal, but by being diagonal, he would have screwed up his variables, right? Because the whole thing was that he had different boundary conditions, which I understand is crucial to everything he was talking about. And so if he diagonalized the system, he would have got very wacky boundary conditions in his variables. For us, we're periodic all over the place. So adding variables to each other and things in a linear combination, we don't screw up our boundary conditions. So I mean, our whole trick is to be diagonal, isn't it? I don't know if what I want to say. If you were to say to me, well, let's do a proper problem where you're not periodic in the vertical, you've got boundary conditions on your temperature and your magnetic field, what does that lead to? Yeah, then I think there might be pattern formation issues, and there might be things to do with binary fluids, and Swift-Hohenberg might show some of those. If you're to say, is that going to shed light on the layering process? That's not clear to me.
Right. Well, I've got more, but can cycle back.
Okay, so we keep you in line. So Steve, I think you're the next one.
Thank you. Nice thought, David. So speaking of Edgar, I mean, he formally showed that another system that maps onto the double diffusive one is the Goldreich-Schubert-Fricker instability at the equator. And so there you get layering. And you also, I mean, I guess this is good news. You also get layering in the 3D system because essentially the terms that you add in, they're kind of just advective terms. So I'm just wondering if when you drop the 2D-ness of your analogy, what kind of terms do you get that break that, that analogy going through to 3D?
Oh, well, So of course yeah, I mean, you break it in a few places. So of course you break it by the Lorentz force, by the tension.
Right.
Okay.
So that's a nonlinear. Is it not?
I mean, the analogy is just the analogy as it stands is a complete analogy for all linear and nonlinear, right?
Yeah. So same for GSF. Yeah.
So, but you're asking what? Sorry, are you asking what sort of terms do I get if
you go to 3D?
3D.
Yeah.
So of course, yeah. So I get a tension term in the.
Yeah.
But also,
okay, but yeah.
You see what you do get, which is very different, is that, and this I don't quite know how it would go through, because if you've got 2D magnetic buoyancy, then the driving gradient, as you know, is B over rho.
Mm.
As you go to 3D magnetic buoyancy, you introduce, so it depends where you are. You can introduce modes for which the driving gradient is B.
Mm.
Okay. So they are modes of a different character. Now you might, unless you are sufficiently far above threshold that B over rho is also destabilizing. In that case, I think 3D, my own feeling is that 3D would go through. You know, if you look at magnetic buoyancy simulations in 2D and 3D, in cross section, they are rather similar. And they have a long wavelength. And maybe that changes things, but yeah, my feeling is that would go through.
Yeah, well, it does for GSF. So
yeah,
yeah.
But you know, without doing it, I can't say more. But that,
and you if you do impose boundary conditions, as you say, I mean, certainly in the 2D problem, you can still get layering in the GSF instability. So I don't think that's, maybe it's more of a worry for your problem than for.
You mean different? Oh.
So if you do, you know, instead of doing a shearing box, you do stress-free boundaries with impenetrable, you know. So I guess the equivalent of your doubly periodic would be a shearing box, and the equivalent of something with, you know, I don't know, proper boundary conditions on top and bottom would be like stress-free and fixed, whatever temperature or something. Then you can still get some kind of layering. It looks a bit different though, at least in 2D. Yeah, 3D is a bit.
Yeah, no, I'm sure that's right. I mean, you know, it would be bizarre if your box was big enough that the boundaries are always fixed. I think the beauty of the periodic boundary conditions is that you know, you don't have, you get layering all the way, as it were.
Yeah.
I guess that's why people do it. But yeah, if the box is big enough, that's right. I'm sure that's true. Yeah.
Okay, thanks.
Okay. Christoph, you're the next one.
Okay, thank you. So I have two questions. The first one is when you have your canonical or natural variables, there is the magnetic variable. And since the convection is turbulent, do you observe something like thermal boundary layers for that canonical variable as well? I mean, the convection is turbulent, so possibly you have thermal boundary layers. And my question is whether you also have substructures for the natural magnetic variable. So that's one question. And the second question is, if you have this layered structure, this staircases, you've got those regions with sharp gradients, and are the length scales of those regions comparable with the length scales of thermal boundary layers? So that's the second question.
Yeah. So there are no thermal boundary layer. Well, okay. So there's no thermal boundary layers, you know, top and bottom, because there is no real top and bottom.
Oh, sorry, that's periodic. Right, I forgot about that.
Yeah. So that's another reason for, you know, by doing this, you get rid of all these horrible complications, Christoph, that you're trying to impose on me.
That's true. Yes. Well.
Yeah, in terms of
all right, so you're not getting boundary layers. That's true. So,
no, but in terms, no, I think the well, that's a good, no, I mean the width of the interface is a sort of, I mean, it's a turbulent boundary layer, so it's thicker than a yeah, it's thicker than a kind of molecular boundary layer based on molecular diffusion. But I mean, that's a good point, and we haven't really explored we don't have very many runs to explore how that varies with
parameters,
with density ratio. Yeah, I mean, that will be the key thing.
Well, thank you. I mean, anyway, Poland is not doing terribly well at the Euro Cup at the moment. It's 2-1 for Sweden, so I was just, I wanted to cheer up myself and talk to you at least for a minute. So
that's called a spoiler. Those things are usually forbidden, strictly forbidden.
You mean saying what is the result?
Absolutely.
Well, it's on right now. Anyone can check.
Do you want to make?
Thank you.
Anyway. You can make some forecasts as well, Christoph, while you're in it.
Forecast.
Yeah,
I don't know.
For tonight's game.
Can the rest of us get questions in before it degenerates to a soccer discussion?
Yeah, I was about to say so. And before Pat strikes, I would like to ask a short one. So if you allow me, Pat.
Sure.
You had this process, David, where you showed that the number of layers was decreasing up to the point there was only one left. And you said that this is not some kind of merging, it's more like turbulence breaking the barriers or something like that. But how does it work exactly? Because is it that a layer just disappears and the others get wider or are shifted radially?
Yeah, and well, how it seems to work certainly in the, okay. So in the 1.5 case, how it works is that the motions in between the interfaces are so turbulent that, that they destroy a turbulent plume comes up and essentially bridges the gap, and that is that. Then it all gets wiped out. For the other one, I don't really know, because the other one is a much, much slower process. So the run which we got, which took us all the way to that final state of layering, that's as far as we got. So in that particular case, I don't know what's going to happen, except that I know from looking at other people's simulations that they always merge. And so what happens is that one is sort of eaten away, and then and the rest sort of spread out to keep spacing between them. I mean, it's a bit like what happens in the Bly model. If you look at the Bly model, then they get those peaks, which are peaks in gradient, which are layers, and they gradually move together and merge. So it's sort of like, and in certain regimes, it is like, Carnot-Hilliard dynamics.
Okay, thanks. So Pat.
Yeah, well, I was going to continue. I mean, static staircases or layers and all seem to me to be sort of a yawner, and all the interesting stuff is in the question of dynamics. So, I mean, really, it's trickier than what you were saying just a minute ago. That in Bly, and by the way, in the drift wave or Rossby wave type of variants thereof, there are in fact multiple types of mergers, right? Depending on whether two guys eat the guy in the middle or just drive him out of existence. I mean, that was an interesting thing. The other question is, In gradient-driven things, of course, we found escalator states, right, where the staircase was, in some sense, moving like an escalator, and it seemed the zoology of dynamics here was nowhere near as rich. Now, you'll say the system may be different, but you have a thought on that, or?
Yeah, I mean, yeah, I have a thought on that. I mean, it's very hard to compare those two things, because if you're modeling a Bly type system, then you can get a system with, you know, a whole load of layers, and you can advance it for a whole load of time, right? And that is almost impossible to do in this system. So it's not clear that the system is not as rich. For example, you can use an enormous amount of computer resources, and when you've had enough, you've got to a state with 7 layers. Okay. In a Bly system, in the twinkling of an eye, you can evolve a system that starts with 50 layers, and you just let it go. And within half an hour, you've done all these fancy things that have merged or eaten each other or whatever. And so it's very hard to make that comparison. I don't think you can just say, oh, it's not as rich, because the equivalent would be, oh, this is the very first stage. This is stage 1 of the Bly picture.
It's a fair point. We're comparing a model to a full crank. So
yeah, you can.
That's an argument for of course developing the model for the DDC.
Yeah. I mean, going back to what you were saying about how they merge in the Bly model, the boundary is crucial.
Right.
Because what happens in the Bly model is that things come in from the edge and eat the first guy there, right? They eat in from the edge. Now that is very dependent on the boundary condition. Sure. If you change the boundary condition in the Bly model and nothing else, then you can get much more stable staircases all the way up to the edge. So, you know, there are these whatever they call them, where they come in from the edge to gobble up the nearest guy there. So that also makes a huge difference.
It's striking. I had actually one or two more. I mean, one never gets the sense. Well, let me delay that. I mean, the question of bistability and bistability of the flux looms large. I suppose that's what Ratko was on about, but it wasn't done. I think wasn't done very well. But let me try something else. Have you ever looked at thermohaline layering with fixed heat flux, and then asked the question, say, of what kind of layers of salt you might get for variable heat flux? This is all done in a fixed boundary type of thinking, as far as I can tell.
Okay, so the short answer is no, and the longer answer, slightly longer answer, is that Guillaume and I have discussed it, and he's on our list of things to do. We have plans. But yeah, I think that's very interesting, actually.
I mean, that's the natural thing, what one would think about from a fusion perspective, yeah, right?
Exactly. Yeah. And that could change things a lot. Yeah.
Okay, Pat, I would propose we move to Guillaume. He has been waiting for some time now, and then we can go back to you if you still have a question. Is that fine with you? Okay, so Guillaume, please.
Well, mine is very fast. Probably a bit unfair, but it's more about curiosity. So sorry. You thinking about for instance, your stellar interior. As you said, you probably have also compositional gradients there. Has anyone tried to add a third gradient and see whether or not those things, under which conditions those things work? Is it a competition between the various diffusivities whose you have competition between several possible mechanisms, and how steady are things if you add what's probably in there in the first place also?
Yeah, I don't know if Pascal and her group have tried to do that. Yeah, you feel it's going to depend crucially on things like magnetic Prandtl number and the diffusivity ratios, don't you? So yeah, and it might depend on, you know, on the vigor of the instability, right? Well, it will, won't it? And so you know,
It's probably, yeah, it's
if you have
probably
a
a question.
if they're all in play, and it's, you know, and it's triply diffusive, one imagines that it will. Yeah, well, that's a good, interesting point, isn't it? One might imagine that it depended on the largest and the smallest.
Exactly, but you have two obvious cases when you have a discrepancy between a very small, a medium, and a fast diffusion, and two of them close enough, and the third one very distant.
I mean, so some people have done some work on this. There have been some papers on triply diffusive things. I can't tell you, I can't summarize the results for you, but some work has, I mean, not here at UCSC, but people have done some stuff on this. And yeah, and of course it depends what the middle one is doing, whether the middle one's helping you or hindering you, right?
Okay.
Nick, but with layering or just?
Oh no, I mean, not in terms of layering, or I don't know. I mean, I don't know the literature well enough. I just know that some of it exists.
Right.
Okay.
Thank you.
I don't see any other hands raised. Pat, you wanted to add another question, or you're done?
I have a few more, but I'll harass David on my own. I don't want to keep everyone from the soccer game. I'll save the long delay for when France is playing. You know, that'd be more.
Okay. Thanks.
Well, then you should carry on, because it's in a short while.
Okay, so I think we are done. So thank you very much again, David, for this nice talk and answering all these questions. So goodbye, everyone. Yes, well done, and see you on Friday. Yeah. Bye.
Bye-bye.
Thank you.